take some notes. Now, I am asking you to please think about doing notes on paper and pencil like you have in the past, up until this last few months. I think it's better for making connections in your brain if you're actually physically doing something. Your brain's been trained to do it that way all your life. And I think it's going back and forth between trying to type things in our Chromebooks or our phones is not making it stick as well. So chapter 25 has been on nuclear stuff, and the section 3 is on fission and fusion. I'm going to take a few bird walks on that journey, but basically you already probably know that our star, the sun, is a ginormous fusion reactor. So inside this huge ball that has 99.8% of all the mass in our solar system, it is almost entirely composed of hydrogen and helium. And that hydrogen is getting turned into helium as we talk. If that huge mass, and just to give you an idea for size, we could put 300 little Earth disks across the equator of the sun, and 1 million Earths would fit inside the volume of the sun. So just like, whew, way ginormous. If it was a giant piece of wood and we were burning it, it would have been gone a long time ago. And so because it's fusion and because it takes a while for the energy to actually get onto the photosphere of the sun, we are able to be alive on our planet. Also notice, ladies and gentlemen, there's a curvature here. Guess what? The Earth is a sphere. It's not flat. Just have to throw that in there for all the science doubters out there, because there's a lot of them. Okay, fission versus fusion. What the heck is fusion? Hopefully you know, fusion's when you put things together. You fuse them together. And in nuclear fusion, or fusing small nuclei, some of you may sew, I don't know, or some of you may know someone who sews. Fusible interfacing, the heat from iron causes the adhesive to stick to the fabric. And this is a quilting square course, but you can still buy this stuff. Fission reactions, on the other hand, fissure means to split apart. So this is when a large nucleus goes apart. So this is a fissure in the ground somewhere near Arizona. And this is a fissure in ice, a crack, a split. So we can put things together. That's kind of like capture. We can break things apart. You can think of it as a decay. We're going to focus on the things that humans are doing. I told you previously that you can't make radioactive decay happen, or you can't predict which atom is going to undergo radioactive decay. You can make more of it happen sometimes. So just a little FYI, also fusion creates a lot more energy, kilogram per kilogram, pound per pound, than a fission reaction. So the holy grail for nuclear power is being able to figure out how to make fusion reactions cost effective. Again, our star is a giant fusion reactor. It would be nice if we could do that here on Earth, but in a contained way. In the sun, hydrogen nuclei, remember hydrogen is just a proton, so 4 protons can fuse and turn into a helium nucleus. So notice, remember, helium nucleus is 2 protons and 2 neutrons. In order to get a proton to turn into a neutron, one of the things that can happen is a positron can come out. And so remember, that's the antimatter of a beta particle or an electron. In that process, a teeny tiny amount of energy is lost, and that energy gets converted into, teeny tiny of matter is lost, and that matter gets converted into energy. Here's an explanation by a couple of scientists on how that happens in our sun. Science shows a little dramatic. They get I don't know. It's so good. They have some good graphics, so I figure it's worth watching.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
With gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
5 million tons of stuff, 5 million tons is hydrogen. And so, fortunately for you and I, the sun has a long way to go before it fades out. And yeah, so that's fusion in the sun. So what about nuclear fusion by humans? Can we do it? Yes, we can. And you know that there are, you know, I've said it a couple times, there are 3 isotopes of hydrogen. The first one is called protium, because all that's in it is a proton. Well, a proton and an electron. 98% of all the hydrogen in the universe is hydrogen 1. There's a little teeny bit of hydrogen 2. So positive proton, positive proton, positive proton. These are all representations of hydrogen atoms because they all have just 1 proton. This hydrogen has 2 particles in the nucleus, a proton and a neutron. 2 things, a duo, deuterium, not spelled the way we spell it, but deuterium. And then this hydrogen 3, has 3 particles in its nucleus, 2 neutrons and a proton. Just like a tricycle has 3 wheels, we call it tritium. We actually call it tritium. So deuterium and tritium are the 2 isotopes of hydrogen that can combine with water to make what we call heavy water. And that can happen because all of these isotopes behave the same way chemically. Why do they behave the same chemically? Because all 3 types of atoms have 1 electron. Okay? Once we have heavy water with these other isotopes of hydrogen, a process can happen if it's rigged in the right way, at the right critical mass and all sorts of stuff, to create nuclear fusion. So D is for deuterium, T is for tritium, and if they collide together with sufficient force and energy at the right angle, all sorts of things, we will very briefly, and I mean very briefly, make helium-5, half-life of 7.6 times 10 to the minus 22nd seconds. A fraction of a fraction of a fraction of a fraction of a fraction. It's like, pooh, you think about it, it's gone, okay? Helium-5 then decays into helium-4, normal, quote-unquote, helium, and a neutron, and a little tiny bit of mass is lost, and that mass becomes energy. And that's what powers nuclear bombs. So we can use this in fusion reactors to make electricity, or we can use it in H-bombs. Controlling fusion is a problem. If we could manage to do it, it would be great because hydrogen's everywhere. So we can unmake water, right? Like our Hoffman apparatus, and we can have plenty of hydrogen available. Also, the radioactive waste is only radioactive for 10 to the minus 20 seconds. So it's pretty safe, okay? The leftovers aren't harmful long-term, and they're not super dangerous anyway, okay? Of course, there has to be problems, or we'd be doing this already, and the problem is to get these to go, to get this process started, we have to have extremely high temperatures. And once they do go, they create even more energy, which makes the temperature even higher. And so then what do you put it in? What kind of container can hold hundreds of millions of degrees? So that's a big problem. The way they do it is with magnets, and they do it in evacuated chambers. This is a tokamak, toroidal chamber. Has to do with torsion, right? So spinning around. So just point this out to you. Here's some people on this top deck, and here's a person down here, just to give you a sense of scale. This is a huge piece of equipment. This is a cutaway, not that it's anything we're going to be studying, but it has a central area that the plasma will spin around in. The cryostat is for temperature, and there's a pump that uses pulsing magnetic fields to push those protons, the plasma, around in there. And we can make it happen. The one at Princeton, I believe this is picture, can make energy, okay? Can make power. And the temperature is 500 million degrees. But the problem is it takes so much energy to get it started. We don't get out even an equivalent amount of energy, okay? It's not more, it's not even equivalent. We get less out than we put in. It's not commercially effective. Another way to do it is to use lasers. There's a big team at Lawrence Livermore Lab, or there used to be anyway, that does laser research, and they were using encapsulated hydrogen to bombard them with laser beams and give them enough energy that they would fuse. But again, super small scale. They could get it to go if they made it happen, but it took a lot more energy in than they got out. It's not commercially feasible yet. Hopefully at some point it might be. You know, we've been working on this for decades, but we'll see if it gets there. All right, so fission is where we get our nuclear power currently, and also nuclear weapons. It splits the nucleus into smaller fragments. The two fissionable isotopes that are used are uranium-235 and plutonium-239. All the old reactors use uranium, which I showed you, those of you that were on campus, I showed you in class, the uranium or the yellow cake. Uranium-235 is lighter than the more common isotope, uranium-238. And so you need a certain percentage to get the reaction to go spontaneously, to create a chain reaction. So they do something called enriching the uranium or uranium fuel. And they do that by spinning the uranium in a, oh my gosh, in a spinny thing. I just blanked out. And those, oh my goodness, I totally blanked out. So uranium-238 is heavier and it sinks. So you guys have probably seen the, maybe you have, I don't know, spinny things for doing blood. Centrifuge, there it is. Oh my goodness. When you spin blood, remember there's solids, the cells in there, they go to the bottom, and the serum It stays at the top, the lighter components of your blood. Same kind of thing with uranium. You spin a sample of uranium, the 238 goes to the bottom, the 235 will be up top, and you can skim that off and enrich your fuel to 5%. We use the higher percentage at our nuclear power plants here in the US. Other countries use this lower amount that has problems. We'll talk about it another time. Of course, plutonium can also be used, and the same kind of thing. You have to centrifuge it to get the right concentration of plutonium-239. I don't have all the numbers for this one, but that is a problem in, say, you probably know, well, maybe you don't. I don't know if you pay attention to world politics, but Iran's kind of on our poopy person list, poopy country list, because they have centrifuges, and we sabotaged their centrifuges years ago, and sanctions and everything. Anyway, they are back at it, enriching uranium, they say, or plutonium, they say it's for their power plants. We say it's for making bombs. But anyway, so these two isotopes can be put in such a concentration in such a way to rapidly decay or fission. This is Hank Green's explanation about who's the first person to figure out nuclear fission. And I just want to check my question here. I'll turn it up. Maybe I'm not talking loud enough either. Are you able to hear now? Well, I hope you can. Obviously you can't if you're not responding. I will be posting the, yes, sorry, it was a connection. Oh, good. All right, so I'm gonna play this. It's a little long, I apologize, but not that much, because I think this is really interesting how we've discovered fission.
Some of the most important scientific discoveries were famously made by accident, like penicillin, plastic, and vulcanized rubber. But there's one that you don't hear about quite as often. That time in 1938, when scientists accidentally split an atom and changed the course of history. At first, they did not realize what they had done. That is, until an Austrian physicist named Lisa Meitner figured out that they had discovered what we now call nuclear fission. But when a Nobel Prize was awarded for the discovery, it was her research partner who got it. Meitner was born in 1878 in Vienna, Austria. Although Austrian women weren't taught much math or science at the time, she was curious about the world from an early age. As a child, she kept a math book under her pillow. She went on to earn a doctorate in physics from the University of Vienna in 1906, which made her the second woman to receive a doctorate in any science from the school. There weren't many opportunities for female scientists in Vienna, though, so in 1907, Meitner moved to Berlin, where she became the first woman Max Planck allowed to attend his lectures. Yeah, that Max Planck, the guy who basically invented quantum mechanics. It was a good time to be a talented physicist in Western Europe. Within a year, she was working as Planck's assistant, and by 1909, she partnered with Otto Hahn, a chemist, to do research at the Berlin Institute for Chemistry. They both wanted to study how different substances produced different types of radiation. There was a problem, though. The head of the institute didn't allow women because he was afraid their hair would catch fire. Not kidding, that's the real reason. Eventually, Meitner and Hahn got him to agree to let them work together in an old carpenter shop in the basement because it had a separate entrance, presumably so that when her hair caught fire, it was really easy to go outside. Research into radiation was still in its early days, so there was a lot to discover. Among other things, they studied what happened to different atoms when they released radiation and discovered some new isotopes, or versions of the same element with different weights. Then, in the 1930s, physicists discovered that if you bombard atoms with neutrons, you can make them undergo radioactive decay, where they release particles and become slightly lighter elements. Meitner, Hahn, and another scientist named Fritz Strassmann started their own bombardment experiments to try to figure out how these reactions work. And then they were interrupted by the Nazis. When Hitler annexed Austria in March of 1938, Meitner, who was of Jewish ancestry, realized that she had to get out of Germany. She escaped to Stockholm, Sweden, where she continued to correspond with Hahn about their ideas and experiments. And in November 1938, Hahn secretly left Germany to share some strange results with her. When they bombarded uranium uranium with neutrons, one of the products of the reaction was what looked like a form of radium, which is a little lighter than uranium. They thought it was radium because of the way it reacted with other atoms and molecules, but they couldn't figure out how bombarding uranium with neutrons would produce radium. The calculations just didn't work out. So Meitner suggested Hahn and Strassmann study this so-called radium more. When Hahn returned to Germany, they did, and found that it wasn't radium at all. It was barium, a much smaller element that's about half uranium.
So what's interesting is he said they react the same way, and that's because they're in the same chemical family. They're in the alkaline earth metal family, barium and radium. We're going to talk about radium after we come back from break, and the Radium Girls is a horrible story. But they both are in the same family, and that's because they have the same number of valence electrons. We're going to spend the rest of the semester and more talking about valence electrons, but they combine with other elements in the same proportions because of those electrons. So
Weight. Hahn and Strassmann were then super confused. They had no idea how neutrons could make uranium turn into an element half its size. In December, Hahn sent a letter to Meitner about their findings, asking for her help explaining them. And in the meantime, he and Strassmann submitted a paper to a German scientific journal describing these surprising results. Meitner's nephew, Otto Frisch, was visiting her at the time, and he also happened to be a nuclear physicist, so the two of them worked on the problem together. Meitner proposed that they imagine atomic nuclei as liquid droplets, which is an idea some physicists were exploring at the time. By thinking that way, Meitner realized that when a neutron hits a uranium nucleus, it could make the nucleus sort of stretch out and then pinch together in the middle and then split in two, like one drop of water splitting into two smaller droplets. She and Frisch calculated that the larger uranium...
So that's a nice visualization, but that's not really what's happening, but it still worked to explain things.
Uranium atom would split into two lighter elements, barium and krypton, plus a whole bunch of neutrons and a whole lot of energy. In other words, she figured out nuclear fission. Since she was essentially in exile, Meitner couldn't publish a paper with Hahn and Strassmann. Instead, she and Frisch published their conclusions in the journal Nature in February of 1939. Fission was an idea with a ton of potential. It was a relatively simple way to produce huge amounts of energy, which is the main thing we use it for today in nuclear power plants. But Meitner realized that it had destructive potential too, and she included a warning about that in the paper. Other scientists were alarmed, especially because they knew the Germans had this knowledge through Hahn and Strassmann. Three physicists in the US then got Albert Einstein, who was already very famous, to write President Roosevelt to explain the danger, and that is how the Manhattan Project that developed the atomic bomb was born. Meitner was asked to help with the project, but she refused, as she didn't want anything to do with using this new science for destructive purposes. After the war, the Nobel Committee awarded the Nobel Prize in Chemistry for discovering nuclear fission to Otto Hahn. Just Otto Hahn. Even though Meitner figured out how fission actually worked, Hahn got all the credit because he ran the experiments that led to the discovery. And it's not like he acknowledged her contributions either. Meitner continued to do nuclear research in Stockholm, including on R1, Sweden's first nuclear reactor, until 1960, when she retired and moved to the UK. In 1966, she, Hahn, and Strassmann shared the US Department of Energy's prestigious Enrico Fermi Award for the discovery of nuclear fission. But it still wasn't a Nobel. 2 years later, on October 27, 1968, Lisa Meitner died at the age of 89. Since her death, she's been memorialized in other significant ways. This is actually way more rare than getting a Nobel. Element 109, Meitnerium, is named in her honor, and so are an asteroid and craters on Venus and the Moon, which is fitting, given that her discoveries shaped a lot of the world as we know it, and her education and research helped pave the way for other women in STEM fields. But above all, she dedicated her life to the pursuit of truth and the peaceful advancement of our knowledge as a species, whether she was recognized for it or not. So maybe the inscription on her tombstone is what best summarizes her legacy: Lisa Meitner, a physicist who never lost her humanity. Thanks for...
So it's important to, I think, for you guys to hear these stories. I know it's kind of silly to watch a video while we're already distance learning, but she, imagine sleeping with a math book, not happening. I fell asleep with books before, but yeah, probably not a math book. But she worked really hard in a time when women weren't allowed to do things. It's crazy, and that separate entrance probably wasn't for her hair. It's so that nobody would see a woman coming into the laboratory. Crazy times. Marie Curie had to deal with it too. All right, so let's talk about fission again. So this thing that they figured out, bombarded with neutrons, uranium-235, uranium's element 92, hit it with a neutron. That neutron sticks if it's going at the right speed at the right angle, and so we still have uranium, 92, the atomic number, but the 235 plus 1 becomes 236. This uranium is very unstable, it falls apart, and when it does, a little tiny bit of mass is lost, a whole bunch of energy is generated, and the crazy thing is more neutrons come out. So you've got krypton, element 36, barium, element 56. 36 and 56, that's 92, right? So these neutrons that go flying out are available to go hit other uranium atoms and make more uranium-236 that also is going to go. And if you get enough of these together, you get a critical mass, you get a mushroom cloud, a bomb. I'm going to post a whole bunch of all the links to these videos. I'm not going to play this one. In a chain reaction, a nuclear chain reaction, there's enough neutrons generated that react with other nuclei that can fission, and more and more and more get generated. So 1 becomes 3, 3 becomes 9, 9 becomes 27, and away you go. It goes very fast exponentially. Okay? And a lot of energy is generated. Famous equation, of course, E equals mc squared. E is for energy. The mass is m. And c is the speed of light. And in some chemistry classes, you actually have to do the calculations. If you use this much uranium with this much energy, mass loss, how much energy would you generate? They can calculate all of that. And of course, the speed of light's super fast. So if you get matter moving fast enough, I guess, it turns into energy. All right, this is just another diagram of the same thing we've been talking about. 1 neutron in, 2 daughter nuclides out, 3 more neutrons that can go off and keep going and going and going. This is humorous. I'm going to show a minute of it. It is probably some physics grad students with nothing better to do, playing around with mousetraps. So some of you probably played with mousetraps before. They're using ping pong balls and mousetraps and setting them up in a big container and setting them off. So, I can't even imagine. If you made one false move, they'd all go off. I don't know how long it would take them. Daniel. So that would be fun. It's kind of like dominoes. All the hard work is setting it up. Boop. I notice they all don't go at once, and just because you knock one of them doesn't mean it's going to start right away. It doesn't have a proper velocity or angle, but pretty soon you get enough of them flying around and everybody's going to go. Yeah, something you can do with your, well, your relatives aren't coming for Thanksgiving, right? Because we're all going to stay socially distanced, but when we get back together again. All right, a couple more things. Why is nuclear power so appealing? Well, 1 ton of uranium has the same energy of 16,000 tons of coal. That's a big difference. Okay. Problem is, this is inherently dangerous to life in its existence. This isn't dangerous to life until we burn it in carbon dioxide in the atmosphere. 80,000 barrels of oil is equivalent to 1 ton of uranium. And the thing with uranium is the byproduct, the stuff that's left over is actually can be used for nuclear fuel. as well, but it's super dangerous and has to be stored carefully. We'll talk about nuclear power plants, like I said, tomorrow. A typical pellet of uranium is about 7 grams. It's borosilicate glass, Pyrex, and then they melt the glass, and then they add the uranium, and then they cool it into these pellets. Little tiny pellets has the same amount of energy as 3.5 barrels of oil, 17,000 cubic feet of gas, natural gas, methane, and almost a ton of coal. That little tiny thing has the same energy content as 1,700 pounds of coal. All right, this is the video that I'd like you to watch for by tomorrow when we meet again. It is a ed puzzle. It has questions you need to answer and submit. It's under 5 minutes. It shouldn't take much more than 5 minutes, I don't think. Where are you guys? There you are. So hopefully that will be a second review going over it, and I'll introduce about power plants as well. Any questions I can answer for anybody right now? Alrighty, well, you're free to go. Enjoy the rest of your Thursday. Thank you.
Thank you.
Thank you.
Thank you. Have a good day.
Thank you too.